We're now starting our chapter on exponential equations and functions. It's chapter 11.2. So first of all, we want to define what an exponential function is. It has the following form. F of x is equal to a raised to the x power. So x is my variable. In the equation form, we can have y is equal to a to the x. Now, this is where a is some constant greater than 0 and not equal to 1. So a has to be greater than 0 and not equal to 1, because if a is a negative number, we will see an erratic pattern in y whenever x is any number. That erratic situation is not a function because, again, functions are predictable. So here's our constraints on the exponential condition. We also consider a as the base number, right? So we're going to talk about a base number in this chapter. So the domain for the function is all real numbers. Note when x is 0, f of x is 1 regardless of a. So in every case, when we have y is equal to a to the 0, regardless of what a is, we just have y is equal to 1. So here's an example of an exponential function. We have f of x is equal to 2 raised to the x power. The domain, you can't really see it, but it's all real numbers. And the range, turns out, doesn't include 0, but all the numbers above 0 to infinity. Okay? And so we can evaluate the function at various points, and here's a table that you can create to look at the evaluation. F of 2 is 2 raised to the second power, which is 4. F of 3 is equal to 3 raised to the third power, which is 8. F of 4 is equal to 2 raised to the fourth power, which is 16. And f to the minus 1 is equal to 2 raised to the minus 1 power, is equal to 1/2. So we're using the laws of exponents to do some of these problems. So now we're going to go to our second requirement for today, is not only defining what an exponential function is, but actually graphing these. Well, before we get to graphing, I have a couple of more examples. I have where a is between 0 and 1, and suppose we have f of x is equal to 1/2 raised to the x power. The domain is the same for this function, and the range is also the same, right? So when we evaluate this function, stop and think with me. So if I put 2 where x is, what should I get? Well, I have 1/2 raised to the 2 power, and I believe that's 1/4, right? I don't believe it, I know it, right? So f of 3 is going to be 1/2 raised to the third power, and that's equal to 1/8, right? So f evaluated at a -1 is 1/2 raised to the -1. Well, what is that? That's just 2, right? We just invert the fraction. We know how to do that, right? So let's talk about that just a second. So 1/2 raised to the 1/2. 1 power is equal to 1/1/2, right? Which we invert and we get 2/1, right? And then finally, we have 1/2 raised to the -2, which is going to be 4, right? Okay, so now we're going to go to our next function, which is f of x is equal to 3 to the x, and the domain, again, right, is infinity. It's all real numbers, right? And the range, again, is going to be 0 to infinity. So that seems to be a pattern for all of our exponential functions, and it's true for all the exponentials. So we could evaluate this function, right, is 3, or f of -1 is equal to 1/3, right? So we could create a table, right, x and y. 0 is 1, always. 1 is 3. -1 is 1/3. 2 is 9. -2 is negative, or no, it's not negative, it's 1/9, right? It's not 1/2, by the way, it's 1/3. So there are errors in sometimes what I do, right? So these tables will be used, can be used to graph the function, right, which we are going to get now. So evaluating the function for a particular value of x helps us also look at the behavior of the function based on x. And that's what we're going to talk about next in the next slide. So now we're looking at two functions, and we're going to graph them. And we're looking at behavior, right? And so we have behavior of points along the line, which we could still do. We could evaluate x, right, like we did before, where we have x and y. And we could go through the process of trying to figure out where the points are, right? And so from this table we could graph our various points, and we notice some very interesting patterns that are going on. So for the first graph, we notice that as x gets larger, f of x gets larger, right? So as x gets larger, f of x gets larger, right? As x becomes more negative, f of x approaches 0. And so when we go in this direction, we see that we're approaching the x-axis, right? So again, the domain is all real, and the range, as you can see, goes from 0 to infinity. Now we're going to see the graph f of x is equal to 1/2 raised to the x power. So again, we can do a table to get a couple of points, but we always know one point for sure on exponentials, and that is what? When x is 0, y is 1. So we always have that point for an exponential. which is the y-intercept, right? Okay, and then from there we can pick a point. We can pick a -1, and we get 2. We can pick 1, and we get 1/2, and so forth, right? And so as x becomes larger, we can see that the graph approaches 0. It approaches the x-axis, right? As x becomes more negative, look what happens. F of x gets bigger, right? Gets larger. Okay? So when we graph these functions, you'll notice two things. One is when a is greater than 0, we have a graph that looks like that. When a is between 0 and 1, we have a graph that looks like that. Our last objective for this chapter is solving equations. So, for equations that have the same base number, the powers must be equal. So we'll look at our first example, where we have 2 to the x is equal to 2 raised to the 5th power. Well, obviously, x must equal 5, right? Because the base numbers are the same, the powers must be equal, right? Again, we'll look at a different problem. We'll look at this particular problem where 3 raised to the x plus 1 is equal to 3 raised to the 2nd power. Well, that means that x plus 1 has to equal 2 and x equals 1. We always want to check our work to see if we got the right answer, and of course that checks out. So now we're going to solve the following examples, right? Here we have 3x minus 1 is equal to 16x plus 2. Well, we can't solve this directly. We have to make an adjustment, and we have to have the same base number. So in order to get the same base number, I will leave the 4 on this side to be the same, but on this side we'll put it as 4 raised to the 2nd power x plus 2. So what we did here, right, is we had the x plus 2 that was raised to the 16th was raised to that, but what we did is we changed 16 to be a base number of 4. And when we did that, that's just 4 raised to the 2nd power. Now, because our base numbers are the same, that means that 3x minus 1 is equal to 2 times x plus 2. Right? So now we have to use the distributive property. 3x minus 1 is equal to 2x plus 4. And so that gives us x is equal to 5. And of course we'll plug it back in, right? We have 4 to the 15 minus 1 is equal to 16 to the 5 plus 7, or not 7, 2. So this is 4 to the 14 is equal to 16 to the 7th. 4 to the 14th is equal 4, 2 raised to the 7th. and so that's 4 to the 14th is equal to 4 to the 14th, and that checks out. So now we're going to look at a new problem. Right, here's our second problem, and again the bases are not equal, but we can rewrite 25 as 5 squared, so we'll do that. So 5 to the x plus 2 is equal to 5 squared x, 2 to the x, and now we can, since we have the same base number, we have x plus 2 is equal to x, and 2 is equal to x when I move x on, subtract x from both sides of the equation. When I plug it in, I get 5 to the 4th is equal to 5 to the 4th, and that checks. That's nice, right? Great problems. So we have a few more additional problems on the next slide. So here's some additional problems. So we'll look at number 1 here. We see that 5 to the x is equal to 1 over 125. Let's see how we can manipulate this. 5x is equal to 1/5 raised to the 3rd power. This is equal to 5x is equal to 5 to the minus 3. Right, so now we have the same base. So x is equal to the minus 3. Right, and you say, well, we didn't have to do all that work, we could see that, but this is the way it would be done if we didn't know how to do the problem. Here we have another issue, right, number 2. And in this case, what we're going to do is here we have 3 over 2 raised to the x, and we're going to rewrite this as 27 over 8 to the minus 1. Now you say, oh dear, that's terrible. But what we're going to do is we're going to do one more step. Here we're going to change this to 3 to the 3rd over 8, or 2 to the 3rd, right, to the minus 1. So let's bring this down to over here so you can see it a little better. 3 halves x is equal to, so here I have 3 to the 3rd over 2 to the 3rd raised to the minus 1. And look at what I can do. This is going to be 3 halves raised to the x is equal to 3 halves raised to the 3rd raised to the minus 1. And so you can see ultimately that x is equal to a minus 3. Right, so x is equal to a minus 3 in this particular case. Right, because 3 times a minus 1, the bases then are equal, and so then the powers are equal. The final problem we're going to look at, Again, we don't have the same basis, so how do we manipulate that? We're going to leave 2 to the 4x plus 3 is equal to 2 raised to the third power times x plus 2. Right, so now the base numbers are the same. And now I get 2 to the 4x plus 3 is equal to 2 to the 3x plus 6. I'm going to distribute the 3. Okay, so now the base numbers are the same again. And so that means 4x plus 3 is equal to 3x plus 6. Right. So that means that x is equal to 3, it looks like, right? Because I subtract 3 from both sides, and so that looks like that's the answer. And we can check it out, but I believe that works, right? Yeah, right, so it's 15, 2 to the 15 is equal to 2 to the 15 is the answer. So that these all check out, right? The last problem is our application for exponentials. And one is a growth problem, and populations typically tend to be exponential in nature. So in this case, the population in the United States can be approximated by the following function, where P naught, which is the initial population of 220 million people for the year 2000, that would be year 0, right? And the growth rate constant is about 1.03. In other words, the population in the United States is growing at about 3% per year. T equals time in years after the year 2000. So we can't really see this very well, so I will rewrite it a little clearer. Right, is equal to P naught times 1.03 raised to the t, right? Where t is our variable, and in this case the domain on t, and we should talk about that. Time cannot be negative, so in this case time for the domain on this particular can be 0, right? It can be 0 here, but it's going in the positive direction, right? So our question is in A, what is the population in millions in 2010 based on this function? So t is equal to 10. And so now we will have the following problem. So here we have P10 is equal to 221.03 raised to the 10th power. And if we did that on our calculator real quickly, we get 1.03 raised to the 10th, and we multiply that times 220, and this is in millions, so we get 295.66 million. This is approximation. So now we will estimate the population for 2016. So again, we evaluate the same function at 16, which is 220 times 1.03 raised to the 16th. And when we try that problem out, we get the following answer. 1.03 raised to the 16th power times 220, and we get approximately 353.04 million people. And these are estimates, right, based on a function. Okay, that's what we do, is we try to estimate based on a function. We try to predict what the population is at any given time based on data, essentially. And so we try to map the data to the function, or map the function to the data, actually, is what we end up trying to do. Anyway, that concludes our chapter 11.2, right? So we've defined an exponential function. We've graphed an exponential function. We've solved exponential equations. And finally, we've applied it to an application problem. So that does conclude our chapter, section 11.2. Thank you.